Hi, everyone. Okay, so in this lecture, we're going to continue along divide and conquer algorithms, and I'm going to give two more examples of algorithms. The first one is medians. So the median of a list of numbers is a number from the list such that half the numbers are smaller and half are bigger. So it's like the central element. If the list has an odd number of entries, then the median is the middle element of the sorted list. If it has an even number of entries, then there's two choices for the median. In our case, so in the case where it's odd, then it's the middle element of the sorted list. If it's even, then we will take it as the smaller of the two central elements. The median has purposes in statistics and because it's less sensitive to outliers than the average. But now let's just think, how do we find the median in an array? One possibility is that we just sort the array and then we, return the middle element essentially. So one way to find the median is sort the array with merge sort. And then two, pick the element, the middle element, if you work it out, if it's an array of size n, is going to be the ceiling of n over 2 of the sorted list. And this algorithm, because it requires a sort, is going to be n log n time. So then we can ask, can we do better than this? Because we're sorting the entire array just to find one element of it. And we'll consider a slightly more general problem, which is we call selection. So in the selection problem, you're given a list of n numbers, s, and a positive integer k, and you want to output the kth smallest element of s. This would solve the median because we just set k equal to the ceiling of n over 2 to return the median. And what we're going to do is we're going to develop a randomized algorithm. And it's going to be kind of different than what we've done thus far, because basically the expected runtime of the algorithm will be better than n log n. But the worst case runtime, if we basically somehow generated the worst sequence of random numbers, will end up being worse. And so it's kind of like in practice, it's better, but it could, in some terrible circumstance, perform worse. It has less strong worst case guarantees. So the idea in this algorithm, it's a divide and conquer algorithm, is we're trying to find the kth smallest element of S. And we're going to split the array into three pieces. I'm not going to say how we split it right now. So just take a number V, and we split S into all the elements that are smaller than V, the elements that are equal to V, if there are any, and the elements that are larger than V. So let me just give you an example. Let's say that we have the array S is 4, 9, 6, 2, 1, 8, 4, 3. And let's take V as 4. V actually doesn't even have to be an entry from the array. It's fine. Then just if it's not in the array, then SV will be empty. But in this example, V is an element of the array. So S left is all the stuff from the array that's smaller than 4. And we don't worry about sorting it. It's not necessarily a sorted array. It's just an array. So we have what? 4, no, 2, 1, and 3, right? So I'll just write it as 2, 1, 3. SV are all the elements that equal 4. There's 2 of them, 4 and then another one here. So it's the array 4, 4. And then S right, all the elements that are bigger, we get 9, 6, 8. And then the reason this can be kind of helpful is, let's say we want to find the 6th smallest entry. So say we want to find the 6th smallest entry in S. So K is 6. What do we know? Well, we know that all the ones that are smaller than 4 are in S left. All the ones that are equal to 4 are in SV, and then all the ones that are bigger than 4 are in S right. So S left these are the 3 smallest numbers, right? These are the next 2, and then these are the larger ones. So since we're looking for the 6th smallest, and S left plus SV only has 5 elements, we know that it's got to be an S right, the 6th smallest, because these are the 5 smallest, right? S left and then SV. So it must be smallest element in S right, since I write, I'm writing this cardinality to denote just the number of elements. So S left plus SV equals 5. Right, so then basically you have 6 minus 5. That's the element you're looking for in S right. And so this is exactly the rule that we're going to use. I haven't yet said how to pick V or anything, but this is the kind of the idea behind this algorithm that we're going to do. And so it looks like this. Let's say we want to find the kth smallest element in S. And we've split it into this S left, SV, and S right. They're not necessarily sorted. If K is less than or equal to the length of S left, then we just search for the kth smallest element in S left. If K is bigger than the number of elements in S left, but it's smaller than the number of elements in S left plus SV. So for example, in this example, if we were trying to find the 4th or the 5th smallest element, then we would just return V because we know it has to lie in SV. And similarly, if we know that if the element we're searching for is larger than S left plus SV, so for example, we're searching for the 6th, but S left plus SV is 5, then we just are trying to find the K minus the number of elements in S left plus SV, that smallest number in S right. So here it's this example, it's the first element in S right. Okay. So now we have to ask, let's say I give you a V. How do you split the array into these 3 pieces, S left, SV, and S right? And what we're actually going to do is try and do this in place. So in place just means that rather than like writing a new array, copying all the elements over, we're actually just going to do swaps in the current array and just rearrange the array S so that it takes the form S left, V, S right. So this function is going to be called split. It takes in S and a V, so an array S and a number V, and it rearranges S into the form S left, SV, S right. The idea for the algorithm is quite simple. It's kind of almost brute force in some sense. What we do, I'm going to make this variable called store, and it starts pointing at the first element in the array. And then I loop over the whole array. I'm going to try and find everything that's in S left. So this is going to be what we're doing here is moving the elements of S left to the left of the array. And then this part, when we get to it, I'll just explain it after, is moving the elements of SV next to S left. And then at that point, S right will be all that's left over. And so it will necessarily be, at the right of the array. So what happens? We start with this store pointing at 1, and we loop through the array. We just check, is the element of the array smaller than V? If it is, then we just swap the ith element with the first element. So we just flip them around, and then we increment that store. So now it points at the second element in the array, second element in the array. Then we find the next one that's smaller, and we again perform the swap. We increment store, so next time it's going to swap into the third, and so on. Now we at this first pass through the whole array, we've moved everything smaller than V to the left of the array. Next, we move the stuff that's equal to V next to S left. So store doesn't get updated. That means it's already pointing at the beginning of this first pass. It's already pointing at the entry immediately after the last element of S left. So then we just continue with the swapping. We check if Si is equal to V, and we do a swap, we increment store, and so on. And at the end, we've moved everything in V next to everything that was in S left, and then by necessarily all that's left over is what's in S right. So, and in this, you notice here, right, we only check the elements starting at store up to N, because we know from 1 up to store, those are all the elements in S left. So in doing this, we've rearranged the array. And you can notice that this algorithm runs in big O of N time. I think that's fairly obvious, because basically it's just a loop through the whole array. And then inside this if, we do a swap. That's an order 1 operation. We increment a variable. So we just do, this is constant time inside the for loop. So this is big O of N for the first for loop. The second for loop, it runs big O of N times. And again, it's just constant time inside each iteration. So we get big O of 2N, which is big O of N. And you can actually see that the way we've written it, it runs in exactly N time, like big O of it. It's also lower bounded by N, because we do have to loop through the whole array. So it's both lower and upper bounded by a constant times N. So now the next question is, how do we pick V? Right? And this kind of told us, if I knew, if I had a V, I could split it, and then I could use this kind of selection rule to decide whether to search in S left, to just return V because I kind of lucked out, or to search in S right. And the way we're going to pick V is that ideally, to narrow down the search, I'd like for there to be an equal number of elements in S left and S right. So we would like to split the array in half. So that S left and S right are both approximately a half of all of S. The thing is, I'd have to inspect all the elements to know what the midway point is. I mean, I'm maybe using this algorithm to solve for the median, so I can't like look up the median to find out exactly how to split it in half, right? The median is the one that does this. So instead, the idea is very simple. I just pick randomly. So idea, just pick V randomly from S. And just see what happens, right? And now we'll try and now analyze what happens. You know, on average, I should pick a number that's sort of near the median, right? Because half the elements are smaller than it, half the elements are bigger than it. It's not like I'm going to hit the median every time, but it's also kind of unlikely that I always get the smallest or I always get the largest, right? I should get something in between. So maybe this works, and we can formalize that idea. I should mention one more thing, that when I wrote split up here, it rearranged the array, but it didn't like keep track of where S left ended and where SV started and where S right started. So I really actually should output two more things. So in the final algorithm, we assume that the output of split is a rearrangement of S. So it actually doesn't even return it. It just manipulates it in place. And then two numbers. So it returns the length of S left and the length of S left plus SV, so that I know where S left ends and I know where S right begins. And then our selection algorithm looks like this. So it uses that selection rule I wrote above, but we take in an array that's not sorted and an integer k, and we want to find the kth smallest element of S. If the array only has one element in it, then, I mean, one thing is that k has to be, I guess, less than or equal to n for this problem to make sense, right? Although you can't find the nth plus one smallest element in an array of size n. So in the case where S is length 1, then k would have to be 1, and this would just return that element, the one element in the array. Otherwise, we randomly select a V from S, and we split the array into the three pieces, sorry, S left, SV, S right. And S has just been modified in place, right? So now S is different. This changed S, and it told us where A and B lie. And then this is exactly implementing the selection definition here, right? Where this S left is A, and this number of elements in S left plus SV is B. So if you look, this is just the selection rule. So if K is less than or equal to A, then we just search for the kth smallest element in S left. Right, so this is just S left. Otherwise, if K is bigger than B, then we search in this. So this is S right here, and this here is K minus S left minus SV, right? And otherwise, we're in that one other case, and we return just V because the element lies in SV. Okay, so now let's think about the runtime of this algorithm. We're going to analyze two different runtimes because it's a randomized algorithm. But first, let's just think about the worst case runtime, which is the typical runtime we consider. Now, in the worst case, we keep randomly selecting, let's say, the smallest element in V, in the array, sorry. So so let's just suppose we are looking for the median. So K is equal to the ceiling of n over 2. Oops. In the worst case, V is the largest element in S each time. And in that case, so the first time we're searching for the median, right? We do this split. V is the largest, so S left contains now n minus 1 elements. SV contains 1 and S right contains none, right? So S left then has size n minus 1, SV has size 1, and S right has size 0. So each recursive call shrinks the array by 1, right? Because now we're just going to search for the kth smallest in SL, right? We just removed 1, and that took us order n time to do the split, right? Split is big, if you remember, it's actually big theta of n. So we get that then the runtime is going to be n. It looks like n plus n minus 1 plus all the way down to ceiling of n over 2. Which is like, it's the, each one of these elements is at least n over 2, and there's n over 2 of them. So I'm going to get like, this is at least as big as n over 2 times n over 2, which is like n squared over 4. So this is n squared. So the worst case runtime is n squared. Now that's not good, right? Doing the sort the array and then just look up the element, that was n log n, and we're getting worst case here of n squared. But the thing is, when you make a randomized algorithm, the worst case is almost always going to be bad, because in the worst case, you like this random generation just turns out terribly. But the probability of us selecting the smallest element in the array every single time is incredibly low. So what makes a lot more sense to analyze is the expected or average runtime. And so for that, we have to think, what is the probability that V is kind of near the middle of the array, and so that we get a good split of S left and S right. And then in our recursive call, we're actually shrinking the array each time. So let's say V is a good like a good selection if it lies between the 25th percentile and 75th percentile. Or I guess I should write 25th and 75th percentile of the array. Then S left and S right have size at most 3/4 of S, right? So then at least if I got like what I'd call a good one, then I know that I shrunk by at least 1/4, right? Like I go from length n to now length 3n over 4. Maybe I luck out and I actually get 1n over 4 because it ends up being in the side that's only 1/4 of the length. But we're trying to just figure out, a bound on how fast this runs. Now notice, I mean, since it's between the 25th and the 75th percentile, we have a 50% chance of getting a good V on any random selection of a V out of the array. So note, a given V has a 50% chance of being good. So then we can ask the question, how many, that's basically now a coin flip, right? So it's like, when I flip the coin, I have a 50% chance of it landing heads. And then we can ask, how many flips do I have to do on average before I get heads? It's more than one. Is it two? It actually is exactly two. So the expected number of coin tosses before heads is shown is 2. So maybe before I do that, how many V's before getting a good one? So, and here I'm saying 2. So let me just give you an argument why it's 2. There's a few ways you can do this. You could actually just go from the definition of expectation, and then you're going to get like, it's going to be 1 times the probability that the first one is heads plus the probability that the first one, like 2 multiplying the probability the first one's tails and the second one is heads, plus 3 multiplying the probability that the first 2 are tails and the third one is heads, plus, and so on. And you get this infinite sum. If you evaluate it, it will come out as 2. But I can give you a kind of clever argument as well that doesn't even require us to evaluate a sum. So let E be the expected number of tosses that I have to do. So if we look at the first toss, it's either heads or tails, right? So if it's heads, then we're done. If it's tails, then we have to repeat. And the key is that a coin is memoryless, right? The coin does not remember that it got tails the first time. And so now that the fact that I've already flipped the coin does not affect the expected number from there to the end. This is like kind of the gambler's fallacy or something, right? Like if you flip a coin and 9 in a row turn up tails, and they're like, oh, the next one's gonna be heads, much more likely. But still, the coin has no memory. It doesn't remember that it just had 9 tails. The probability that the next one is heads is still just a half, right? And so because of that, the coin is memoryless, we get the following. We get that E is 1 coin toss. So the expected number of tosses is 1 plus, with probability 1/2, I'm done. So I don't have to do any more. Plus with probability 1/2, I have to basically start the whole experiment over again. And so I will still have the same expected number of tosses to go. And so this is just then tells us that 1/2 E equals 1 or E equals 2. Okay, so the expected number of coin tosses before heads is shown is 2. And again, like I said, you can also just go from the definition of expectation and just write out all the probabilities, and you'll get this infinite sum that evaluates to 2 if you don't like this argument that much. So from this property, though, we see that in every 2 splits, we get a good one. So, and when we get a good one, we reduce the size of the array we're searching, either S left or S right, by at least a quarter. So the new one is at most 3/4 of the size. So we get then that Tn, this is now, in fact, why don't I write it as the expected time on an array of size n. This is expected time is less than or equal to when I make a recursive call. Let's just look back at our algorithm. So selection, right, SK, it only makes one recursive call. It makes the call to this, search S left if K is less than or equal to A, and it makes a call to search S right otherwise, right? So we only make one recursive call. That's why down here there's a 1 out in front. The call searches array of size at most 3/4 of n. That's why I'm writing less than or equal to here. And then plus big O of n. And so this is the time on the smaller array. And this is the time to do 2 splits. And so this is an expected time, right? And sorry, here, this should be an E, because I wrote an E on the left, right? The expected time to run on a array of size n is 3/4 n plus big O of n. So on average, 2 splits, each big O of n to reduce by 1/4. Now, if we solve this recursion from the master theorem, we actually get big O of n. And so the selection algorithm runs in n squared time in the worst case, but its expected time is big O of n, which is linear in the input size. And in some sense, that's the best you could hope for, because to find the kth smallest element in an array, it seems reasonable that I have to look at every element of the array to figure out if it's the kth smallest. And so I can compute min, max, median, anything with this algorithm, and they all run in big O n time, which is kind of cool in an expectation. In the homework, we talk about the quick sort algorithm, which actually operates similarly to merge sort, but kind of using the ideas from median. So it uses split, the one that we just talked about, to divide the array at a random point rather than splitting in the middle like merge sort does. In practice, it typically outperforms merge sort. And so in the homework, you're going to exactly do this if you haven't already looked at it, but look at the worst case runtime, which is not going to be so great, and then look at the expected runtime, which should be on par with merge sort, but in practice actually operates faster. I'm going to now very briefly give you one more example, but here, don't worry about the details so much. I just want to give you another example of a divide and conquer algorithm. The main thing is just going to be to write the recursion relation. So I wouldn't even worry about the particulars that much in this example. And it's actually really complicated, but I think it's kind of a cool result. So let's say we want to multiply 2 n by n matrices, x and y, and get their result at z. You know, right, when you want to multiply matrices, you take, like, to get the 1, 1 entry of the resulting matrix, you take the first row of x multiplied by the first column of y. To get the 1, 2 entry, you go the first row of x multiplying the second column of y. And so to get the ijth entry of z, you have to compute this product, where this is ranging over the ith row of x and the kth column of j. Or sorry, the jth column of y. Sorry, let me say that again. The ith column of x with the jth column of y. Geez, I don't know what I'm saying. Let me write it because I feel like I just bungled that. So this is the ith row of x, and this is the kth column of y. That is, we perform a dot product between the ith row of x and the jth column of y. So how many Z, if these are two n by n matrices, then we know that Z has, we have to compute n squared entries. Because you have Zij for ij from 1 to n. And for right now, this is a little different than when we've been talking about like multiplication of large binary numbers. Here, we're not thinking that the entries in Z are big. So the matrix can get big, but the entries are just like, 16-bit ints or something like that. So multiplication of two elements of these matrices can be done in order one time because it's just like a constant time operation. So assuming each entry has a value independent of n, we have these multiplication is constant time, but to compute a Zij, I have to do this n sums, right? So it's order n time to compute Zij. So Zij requires n additions, implies big O n per entry. And we have a total of, like I said, so n here is not the number of bits in each number, it's the size of these matrices. And we're thinking about how does this operation scale as the matrices get bigger, not as the numbers in the matrix get larger, right? So that's why I'm saying it's only order n time per entry. And so overall matrix multiplication is n cubed time. We're thinking about scaling in terms of the size. And so then there's the question, can we do better? And there's this very cool algorithm to do this, and I'm just going to give a quick overview of it. It's a divide and conquer algorithm. And the idea is to break x and y into 4 blocks. Each one is an n over 2 by n over 2 matrix. So these are kind of my blocks like this, A, B, C, D for x, and then this should say y. Right, this should be y equals E, F, G, H. And now, so rather than thinking of multiplying these 2 n by n matrices, I now have 8 n by 2 times n by 2 matrices. And if I write out what the multiplication looks like, so each one of these matrices is n by 2 by n by 2. And if I just write out the multiplication of x times y, it looks like this. You go A times E plus B times G. This one's A times F plus B times H, and so on. And then the clever thing that someone named Strawson realized is that I can write, if you look at what I've done here, right? This looks like I have 1, 2, 3, 4, 5, 6, 7, 8. 8 multiplications, multiplications of n over 2 by n over 2 matrices. If you were to write out the recursion relation, where instead of doing one multiplication of n by n matrices, I do 8 of n over 2 by n over 2, and you write out the recursion relation, you get n cubed runtime. It doesn't help. But what this clever person realized is there's actually a way to do it where I only have to do 7 n over 2 by n over 2 matrix multiplications. And it looks like this. So I define these 7 different products, P1, P2, P3, P4, P5, P6, P7. And then this first entry, AE plus BG, can be written as P5 plus P4 minus P2 plus P6. CE plus DG can be written as P3 plus P4. And you can verify these if you just plug in P3 and P4, right? This is CE plus DE. And then I'm going to get minus DE plus DG. And so it's going to just be CE plus DG. This entry is correct. You can verify for all of them. But the thing that's very cool is that it allows us to compute X times Y using just 7 n over 2 times n over 2 matrix multiplications instead of 8. And so we can recursively apply the rule just like we did in our divide and conquer multiply algorithm. And we get a recursion relation that looks like the time to multiply 2 n by n matrices is 7 times the time to multiply n over 2 by n over 2 matrices plus big O n squared time to combine their answers, because I have to do these sums, right? And each of these matrices has n squared entries in it, or order n squared entries in it. And so if I look up in the master theorem, you're in the case, so this is the case where, so A equals 7, B equals 2, D equals 2. Look it up. You get big O of n to the power of log base 2 of 7, which is big O n to the power of 2.81. And so this algorithm is able to improve the runtime from n cubed using the kind of basic idea that we would all do down to this by removing one multiplication, get it down to n to the power of 2.81. So it's just a cool, I don't know, just a cool thing. The only thing I would say is you don't have to memorize anything to do with this. It's just, how do I get if I give you an algorithm, how do I get the corresponding recursion relation and find the runtime? So that's all for this. In the next lecture, we'll look at the fast Fourier transform, which is our last divide and conquer algorithm. So thank you, everyone.